Howdy, everybody. Thanks again for joining me in this video where we're going to chat about our Unit 4, our waves and optics. You can see when I'm recording this because I forgot to delete it this time. I'm actually curious, did I forget in the other one? I'll also have a link in our D2L course, but if I put this on YouTube, I'll probably have the view links there as well so people can snoop in on these if they ever want to look through my chicken scratch horrible notes, which will be of varying quality, and I'm always learning and improving and making mistakes, and I hope that y'all are doing the same. It's really required for learning and growing. But let's get into it. Let's talk about, we've done through our electrostatics allegedly at this point, and our circuits at this point, and our magnetism at this point, and we found that changing electric fields create changing magnetic fields, create changing electric fields in perpetuity. And when we really get to this in full detail, we'll go through some of that math. I won't expect you to do it. It's a lot of these weird fun vector properties, some of the stuff that I did in the course that follows this, intermediate E&M, and again in advanced E&M, and of course things you would do as a physicist or as an electrical engineer or maybe as a mathematician if you were doing like an applied math master's kinds of things, because it's a lot of good examples within some of those pieces. So keep all of that in mind, that much of this, even when we get into the like low altitude view on the ground, us doing these pieces for real, a lot of the derivation steps especially, I'm not going to expect us to be able to do. I'm going to expect us to kind of show up, to understand, to appreciate it, to build some tolerance with that space and start getting used to some of those techniques. And really, unless we're a mathematician, a physicist, an electrical engineer, many of these pieces may not even come back at all, and certainly would only come back, I would say, at the experimental / application slide, which is where we'll do a lot of our actual work in classes on, okay, now that we've gone through some of this theory, where some stuff is coming from, let's chat about how it's actually used, what we can actually do. And this is where we tend to find that units 1 and 3, our electrostatics and magnetostatics units, tends to be the mathier pieces that people are like, this is crazy. And units 2 and 4, our circuits and our waves and optics, tend to be a little bit more plug and chug at some level, and a lot of people feel a little bit more confident with them. I'm hoping that throughout all 4 units, we're able to help develop a more robust and deep understanding of how some of these pieces work and fit together. So without any further ado, let's get into it. We're going to talk about this so-called wave equation, what it looks like in the structure of it. I'm actually not going to write it out right now, but we're going to talk about that wave equation, what it means, and different types of waves. So wave equation and types of waves. And the big 2 types of waves that we're really going to talk about are called transverse waves, which light acts like, and so do waves on a string. And even waves in water, at least most waves in water other than sound waves. The other ones are called longitudinal waves, which is like sound waves. That's typically what we think of, where the direction of propagation is in a particular direction, but also the direction of wibble wobble, because that's really what a wave is a wibble wobble that travels. So the wibble wobble that travels is going like this, but it's drifting in one particular direction. That's basically what sound does through whatever medium it's carried in. Versus a transverse wave, whether it's a wave on a string, you send a pulse, and then that whole pulse kind of moves this way. The motion up and down on the string is perpendicular to the direction of propagation. So that's your light waves, that's your sound, or not sound waves, that's your light waves, it's your string waves, those kinds of pieces. Water waves, the conventional, like boats on the ocean kinds of waves work like that. And what we're going to really delve into, again, is in the context of light, these transverse waves and the properties that end up emerging with that. Where if I have this wave that's kind of like this, and I have this wave traveling this way, and it's traveling with another wave that's also traveling this way, when those waves meet together and they stack up on top of each other, they're going to make a bigger wave. This is, in general, the idea of what we call superposition. And specifically what this leads to is this idea of constructive interference. Interference being the other big word, interference. And what we find is that if these waves arrive out of phase with each other, phase being another big word that we often talk about, and so to picture what I mean when I say out of phase, let's see if I can extract just the black wave here. Or just the red one. There we go. So if they arrived like this, where this one is up when this one is down, they actually are going to flatline, or at least one of the waves is going to win if one of them has a bigger amplitude. Amplitude being the size of the wave, another where that hopefully we remember a little bit from trig, where again, trig's another good place to go back to. Every sine wave looked like some sort of amplitude value times the trig function times some sort of frequency value times some sort of piece that wibble wobbled, plus a phase shift, plus a midline shift. And what we're going to end up finding with light in particular, this midline shift we never really worry about because the light is always wibble wobbling up and down. It doesn't really have that so-called DC offset, but electric waves, electric signals could if we were dealing with those sorts of waves, which in this class we won't really beyond some very basic alternating currents, which again will look kind of like this, but with time in here. What we're going to find with light is that light actually varies with both time and so it's got to have like an angular frequency associated with that time, how quickly it rotates through the time space. But then it's also going to have a spatial frequency, a so-called wave number, which I'm so sorry we use the letter K for, times x. And then this plus or minus at some level is going to dictate the direction that it travels along, but it also is a vector. It has to point in a particular direction. So maybe it's polarized in the x direction, or sorry, in the y direction, but it's moving in the x direction. And we'll talk similarly about, well, if that's the case for this is what the electric field looks like. So I'll put a unit here to say this is the magnitude, the amplitude of the electric field. And this is what your electric field looks like as a function of time and space. Your magnetic field is going to have a very particular structure that follows this thing we call the pointing vector. Pointing vector. It's somebody's last name, but it also conveniently points in the direction of energy propagation. So it's going to be equal to E cross B divided by mu naught to make the units work essentially. Has units of intensity, which is like power per area. So if we multiplied this by an area, it's essentially a idea of flux, of light flux. And we'll talk about that as well in other applications when we talk about things like solar sails and astronauts being able to push themselves with like jet engines, but instead of throwing out fire, they throw out light, and it's a small force, but we'll be able to calculate it and do some, I would say, theoretical experiments, some calculations. Fortunately, it's such a small force, we can't really do good experiments with it on Earth. But these are some of those pieces that, we'll end up using some more right-hand rules with some of these pieces. We'll revisit other pieces with interference where we'll talk about like thin slit interference and Huygens principle. I want to talk about Huygens principle because that's kind of the thing that underlies everything. It's basically this idea that if you have any wavefront that hits some sort of new interface, each little different spot inside of that interface is going to re-emit as though it were a spherical wave. And the way that those stack up on top of each other is going to dictate what sort of interference you have. So if these slits are really small, it basically becomes just one point and it re-emits as that. And if you have a wall here and then a second one spaced a little bit further apart, you have two of these individual point sources that now interfere with each other. And we'll learn some other math about how to do this and predict this. And what's really interesting is even in quantum mechanics, what we'll find is non-wave-like things in certain circumstances exhibit this wave-like property. Light, in this case, is a true wave, But at some level, it also is a particle. We've heard of these things called photons. And this is, again, one of those places where we're really butting heads with both special relativity and quantum mechanics, kind of either like E&M is really the subject that led us to discover both of those things, of course, coupled with chemistry. And I always like to reinforce that because truly, we could not have figured out quantum mechanics without both physicists and chemists working together to kind of meet in the middle and figure out some of these ridiculously complex and just viscerally strange things. It's strange because we don't see them all the time, and as we start seeing them more and more often, we can build some intuition. But even still, like developing true intuition with quantum mechanics is just near impossible to do, to the point where I don't think anybody, any human on this planet has ever really had a true understanding of quantum mechanics. It's just so counterintuitive to our everyday life. But the more exposure we get to it, the more comfortable we get with modeling it and building some intuition. Again, not a perfect intuition, but in many cases, it also humbles us as well to realize we never really had a perfect intuition of classical mechanics either. If we were missing many of these pieces and learning in phys 1 these things like a centrifugal force, it really feels like that force exists, but it's a fictitious force. It's that we're not in an inertial frame, and the way that our rules have to adjust are very different. So different that we don't even really learn them in a Phys 1 class. We just kind of say, shut up, there's no such thing as a centrifugal force. And we just gaslighting is the strategy there. But in like the follow-up course, just like there's a follow-up course to this, intermediate E&M, I don't know if mechanical engineers take it, but certainly physicists do, like an intermediate mechanics course where we talk about those coordinate transforms and we see how when you mathematically go into a rotating coordinate system in the rotational frame, you get something that looks like a force to that observer. It's not an inertial frame, so we don't call it a true force, but that force does, quote unquote, exist in that non-inertial frame. So I think those are many of the big pieces. Depending on what time we get to, we'll talk some about more geometric optics, things like we'll definitely talk about reflection and refraction. So reflection being this idea that if you have like a flat surface and light comes in at an angle, we always measure angles relative to, I don't like that it moved my color around. We always measure angles relative to the normal. So this would be like the angle of incidence. The angle of reflection is always going to be equal to the angle of incidence. It's kind of just a fact. We don't really delve into why that's the case, but if you look at Maxwell's equations, this does have to be true. It's a longer process. Again, it's why there's follow-up E&M courses. But this is also then if you have certain types of mirrors, like I have a parabolic mirror, and I work through this math with this very particular parabola and this very particular so-called directrix and focus. Basically what happens, they bounce in and they always go through this focus, which means the inverse happens. If you had a light bulb at this focus, these waves out here are going out spherically, but all the waves that came backwards, this one bounces out this way and this one bounces out this way. And so this is how you can make a mirror redirect. If you look at your car headlights, many of them have this geometry where it takes a lot of this energy and redirects it forward so that you can see further. And even back in the day, like famously the lighthouse at Alexandria in Egypt, they had this like bonfire, but you can't see the bonfire from very far unless you have this big, very shiny sheet of copper that's been very carefully pounded into this parabola. And then they could use this to signal ships far away at sea, like, hey, there's some rocks here, don't crash. It's a better way of redirecting some of that energy. So we'll be able to talk about some of those things with mirrors and lenses if we have time. Most of the time we end up just doing some of this more fundamental geometric kinds of pieces. And the other piece, there's this reflected part of the wave. There's also a part of the wave that gets refracted through. And so when it transmits, this is what we call that refraction, where this angle of refraction is going to be different depending on what type of material it's in. So for instance, if we go from air into water, we categorize these different materials by this thing called the index of refraction, where air is basically 1. It's like 1.007-ish, plus or minus a few, depending on in certain environmental factors, versus water, which is roughly like 1.33-ish something. And that's what makes it bend. In this case, it's going to bend towards the normal. But if you had something here, a light wave coming in, and it was escaping, it would actually bend away from the normal. According to this thing we call Snell's law, it's going to have this mathematical form of in1 sine of theta 1 equals into sine of theta 2, which for a while was just a mathematical modeling thing that we're like, hey, we collected a bunch of data, we did these experiments, and it seems to follow this. And it wasn't for like, I want to say 20 or 30 years until the reason why we call them the Maxwell equations, until Maxwell played with all of these equations and put together from pure theory where this equation and other phenomenon come from. It's why we give Maxwell the credit for 4 equations that he didn't make. He did make the Maxwell correction term on Ampere's law, that piece that was missing with the displacement current. That is named after him. But there's a reason we name all of the equations after him, and by a reason I mean there's like 20 different reasons. He really put together a lot of these math and physics pieces into one convenient, nice package that kind of contained just a lot of the truth of the universe. And by the end of his life, he set the stage for folks like Einstein and Hilbert and other early folks to, be hot on the tail of special relativity and quantum mechanics that are coming from these pieces. So that's really where we wrap up. It's typically about half the size of a unit of the other pieces for this last little sprint here at the end with optics and such. And it tends to be most people's at least easiest. Not everybody's favorite. Typically, people's favorites are either magnetism, which is interesting because it's also typically the hardest. But when you see it again, because it's so similar to the electrostatics, you kind of get that extra confidence of like, okay, I've learned how to fail forward a bunch of things, and I'm seeing some patterns work together, and I've already figured out a lot of these like density things and symmetry things, and you just kind of get to have that second victory lap of pieces. Even though it's harder, it often doesn't feel as hard. Or circuits. Circuits tends to be a little bit more direct, more applicable. But and I love all of them. For me, it's like a parent choosing between their favorite children. Like I truly do love all of these pieces, and I love them more as I realize how they work together. And I'm always learning and seeing new levels, new details. So that's kind of the big, quick overview of everything that we're going to cover in this entire course. Forget the sum of the total videos lengths here, but 2-ish hours maybe. And we'll get into more details of everything over the next, like 4-ish months is a typical semester, unless this is being done in the summer, and then it's like, 2.5, depending on the curriculum. So in any case, I'm excited to get to do this journey of E&M with you and share truly one of my favorite things in the entire world. So until next time when we delve into more and more detail, or until the other videos that I record where we read through the textbook together. Till then, have fun, and if you can help somebody else, help them. What's the thing on one of my favorite podcasts they're always saying? It's overdue, a podcast about the books you should have read. At the end of it, they're always saying like, take care of yourself, and if you can, somebody else too. And I think that's a good way to live life. So till then.